Solving trig equations using square roots. So I've got this equation here I want to solve for theta. I will be using the calculator and getting decimal approximations. We're working in terms of degrees and we only want solutions between 0 and 360. Of course, I'm always starting with trying to make the equation look like that simple format, and I'm a little stuck here because I have a tangent squared theta. I don't want that. Factoring just isn't going to work. You could move the 14 to the other side, but what you have left is not factorable. Another technique that can work involves using the square root method, especially when you have a trig function squared. Here's how that method works. For the square root method, I don't want a 0 on one side. I actually want to get rid of everything except the item being squared. So I'm going to add 3 to both sides, and I'm going to divide both sides by 6. And remember what tangent squared theta actually means? If it helps you, you could write out what it means. It means that the entire tangent theta ratio is being squared. Well, that's great because algebraically I know that to reverse that squaring, I can simply square root both sides, provided I remember that there are always two solutions, two possible solutions when I do that. The left now is simply tangent theta. The right is plus or minus, and I think I will break that up, square root of 17 over square root of 6. Do you see that once again we have taken a complicated equation and we've split it into two pieces? I have tangent theta equals positive root 17 over root 6. That fits the pattern that we wanted. And then I also have tangent theta equals negative square root 17 over square root 6. I'm not bothering to rationalize the denominators there because I know I'm just going to go to the calculator eventually. We have completed step A by turning this complicated equation into two simple equations. And now I can move on to step B. I'll have to do it twice. So for the tangent function, remember the period of the tangent function is only 0 to pi or 0 to 180 in degrees. So in my tangent pictures, I never have to look past just these first two quadrants. Let's see, for the first picture, I want tangent to be positive. Well, tangent is not positive here, so that means I'm drawing a first quadrant picture. Let's see, tangent ratio is opposite over adjacent. Here's the angle in question. This is obviously not a special triangle, which means in order to find that angle theta, I'll just go to the calculator and use the inverse tangent button. Now, is that going to give me what I want? It will. Inverse tangent knows about first quadrant angles between 0 and 90 degrees, so it will give me the angle that I desire. Tangent inverse of that fraction. Okay, we'll go to the calculator. And I need to put myself in degree mode, so let me make sure and do that. Okay, and then we can just go ahead and type it in. So we're doing tangent inverse. I have square root of 17. I'll arrow out and then divided by square root of 6. And again, arrow out, close the parentheses. And I end up with about 59.3 degrees. Remember, step B is to find all the solutions within one period. The period of the tangent function is pi, or 180 degrees, so I only needed to find that one solution. Now I'll move on to the second equation. Tan theta is the negative version of that fraction. Well, obviously this one must be in the second quadrant. The first quadrant tangent is positive. I'm only ever looking at quadrants 1 and 2 for the tangent function. I'll have a very similar picture here. Let's see, the negative must go here since the x value is negative, so root 17 and then over negative root 6. Here's the angle I'm interested in. So can I just go to the inverse tangent button on my calculator and get that angle? Unfortunately, no. The inverse tangent function has never heard of angles in the second quadrant. The inverse tangent button only knows about angles between negative 90 and positive 90. So I'm going to have to do some thinking here. Let's see, negative 90 to positive 90, that's first quadrant and fourth quadrant. Isn't there another symmetrical triangle picture right here in the fourth quadrant where I'd have all the same pieces? I suppose this would be negative and the root 6 would be positive, but the ratio would be the same. You see, what the calculator is going to give me when I go there for the inverse button is this angle. Because again, it only knows angles between negative 90 degrees and positive 90 degrees, the inverse tangent button. Let's go ahead and get that angle, and then we'll try to figure out how we can get the angle we actually want. So to find the green angle, we're going to do tangent inverse of that negative fraction. That should be easy enough to do on the calculator. In fact, what I can do, I can just use that entry command above the enter button, and then I'll just go over to the front of that square root and I will insert a negative sign and hit enter there, and I've got negative 59.3 degrees. I guess that shouldn't be too surprising if this angle here was positive 59.3 degrees. Of course, this one's going to be negative 59.3. It's the same triangle, just in a different quadrant. Okay, but negative 59.3 is not the angle I wanted. I wanted this red second quadrant angle. How can I get that? Well, there's a couple of different ways you could think about it. One way would be to use reference triangles. I mean, obviously, this little angle here is the same as this angle here. So this is another 59.3 degrees. All I have to do to get the red angle then is subtract 59.3 from 180. And that's going to give me about 120.7 degrees. Another way that we could have thought of it, look at these two angles. You can tell they're exactly opposite each other, which means they're 180 degrees apart. So I could have just thought, oh, just take negative 59.3 and add 180. And if you do that, you will also get 120.7 degrees. Okay, are we finished? Do we have to do part C? Well, yes and no. This one's a little tricky. I don't want all the solutions, but I do want more than just one period. So far, we've only found the ones between 0 and 180. So I'm going to have to at least think about part C in order to get all the answers that I want. Here's what I mean. We know one answer is 59.3 degrees. But we also know that if you keep adding multiples of the period's 180 degrees for the tangent function, you'll get more answers. So I'm going to have to add 180 to that. When I do, I get 239.3. Well, that's still in the interval that I'm looking for, so that must be an answer too. Well, what if I add another 180 onto this? That would be too big. That would put it over 400. That's outside of that range. So I know I don't need any more from that first answer. Then my second answer, remember, was 120.7 degrees. Well, I'm going to need to add 180 onto that. That comes out to be 300.7. Remember, I can add as many 180s as I want to these angles to obtain more solutions. That's in the range, but obviously if I kept going, I would be way too big. I'd be up in the 400s again. We have found 4 possible solutions to this equation, and these are the only solutions in the interval 0 to 360. Thanks for watching.